In section 9.3, we are going to be looking at how you can reach goal amounts in saving your money. The first idea for this is you are going to put one lump sum in the bank and allow it to grow until you reach your desired amount. For example, what if you wish to retire with $1 million in your IRA? How do you make sure you reach that goal? In this case, you are trying to decide how much should you put in the bank today in order to have $1 million when you are ready to retire. This will require the use of the first formula that we're going to look at. Our formula for present value is PV equals A over the quantity of 1 plus R over N being raised to the NT power. Please take note that this is the formula that we learned in section 2 of A equals P times 1 plus R over N to the NT formula. We have just taken that formula and solved it for the P, and we renamed P as PV to stand for present value. To do that, we just divided both sides by the parentheses, and that's how we got this new formula. Our example to use this formula says Sam wishes to have $40,000 in 5 years to purchase a car. How much should he put into the bank today in order to achieve his goal if his money will earn 3.2% compounded quarterly? What's really important to note here is that we are putting the money in the bank today. If you think about that wording, that means that we are going to put one chunk of money into the bank today, and we're just going to let it sit there and grow. That's what's going to tell us that we need to use this formula. We are only putting in one deposit and letting it sit and grow. Make sure that you go ahead and find R over N and NT before you begin working this problem, because otherwise the calculator work can get very, very complicated. So doing those ahead of time makes your calculator work much, much easier. R over N for this problem, 0.032 divided by 4, because it says quarterly, will give us 0.008. N times T means we need to take 4 times 5 years, which gives us 20. If we put all this together and put it into the formula, our goal amount is $40,000. So that's the A. A is always what you want to have down the road in the future. In the denominator, we would do 1 plus 0.008 and then raise it to the 20. 1 plus 0.008 is just 1.008. So doing that addition, we will have 40,000 over 1.008 to the 20. Put this into your calculator exactly the way it's written. Put in the top, hit your divided by key, and then put in the 1.008 raised to the 20. You should be getting 34,107.46. Now let's think about something. You want to have $40,000 down the road in 5 years. In order to do that, you would have to put $34,000 in the bank today. Well, if you already have $34,000, wouldn't you go ahead and just buy the car now or do something else with that money. Most people don't have $30,000 as a chunk of change just sitting around. Mathematically, this is what you would have to do to reach that $40,000 goal. You'd have to put $34,107.46 into the bank and not touch it for 5 years. Most people in the real world can't do that. So while this is what you would have to do mathematically, it is not realistic. So what do we do if we don't have $34,000 in change to sit in the bank? We can create what's called an annuity. An annuity is an account in which equal payments are made at equal periods of time. If you go strictly by the definition, then if you are making a car payment, that's an annuity, and a house payment, that's an annuity. If you are saving money by putting $100 into the bank every month, that's an annuity. Here's our first formula that we will be using with annuities. In this formula, we will be finding the future value for an annuity, and that equals the payment times this fraction that looks very complicated with the numerator of the quantity 1 plus r over n raised to the nt minus 1, and then you have to take that divided by r over n. You are going to use this formula when you know the monthly payment, the quarterly payment, the semi-annual payment, what we call the periodic payment, and you need to find the future value for this account. Example 2 is a situation when you would need to use this new formula. In order to save for retirement, Jessica is going to deposit $400 every 3 months into an account that earns 2.46% compounded quarterly. How much will be in her account in 40 years when she is ready to retire? Things to watch for on this to help you decide that it is this formula and not the first formula. We are depositing $400 every 3 months. If you think about that wording, that's telling you this is happening more than once. That's the key difference between this formula and the last formula. Deposits happen more than once. The part that tells me that its future value is how much will be in her account. It's not there yet. We're trying to get to that. If you go back and look at this formula, it's very complicated having r over n and nt in it, and trying to put in those fractions within the formula would be horrible. So this is where you really have to do r over n and nt first, because the formula just gets so messy if you don't. On this problem then, r over n, our rate is 0.0246. We are compounding quarterly, so we're going to divide by 4. So r over n comes out to be 0.00615. N times t, how many times a year? 4 times a year. How many years? 40. So n times t is 160. Now let's put everything into position in the formula. We're looking for the future value, the goal amount. What's our payment? Our payment is $400. That's what you're doing periodically. In our bracket, we have that 1 plus r over n again. 1 plus a decimal is just 1 point whatever. So we're just going to go ahead and write it as 1.00615 to the 160 minus 1. All that goes in the bracket, and then over the r over n we found, 0.00615. By finding those decimals in the NT ahead of time and then putting it into the formula Now the calculator work is easy. Put in your 400 times, there's brackets in the formula. You don't have brackets usually on your calculator. Some do, some don't. So just use the parentheses that's on every calculator. Then put in the entire inside as it's written. Most of you have a caret for your exponent key. Close your parentheses and then divide by 0.00615. In doing that calculation, you should get 108,428.37. At the end of 40 years, and all these deposits and all the interest earned, the account would have $108,428.37. Is somebody going to be able to retire and live on that? No. Maybe for a year or two, but that's about it. On the other hand, if you think about what was actually deposited, Jessica was doing $400 4 times a year for 40 years. If we multiply all that, we get 64,000. So in actuality, she put $64,000 of her money into the bank. But at the end of the 40 years, she had $108,428.37. All of that extra money in that account has come from interest. She's made deposits on top of money that already had interest, and then that money earned interest, and so on, to the point where her money almost doubled because of interest. Our next question: what if we know our goal amount, but we don't know how much each deposit should be in order to reach that goal amount? In that case, we solve the previous formula for future value of annuities for payment. Our annuity formula for finding monthly payments or quarterly payments or whatever the periodic payment is future value equals this fraction of R over N, all of that over the quantity 1 plus R over N to the NT minus 1. I just did algebra on the previous formula and solved it for payment. On example 3, we are somewhat revisiting example 1. Sam decides that the single deposit required in example 1 is not feasible and opts to instead deposit money every month in smaller amounts to reach his goal of $40,000 in 5 years. If his account will now be earning 1.5% compounded monthly, how much should each monthly deposit be? So how am I going to tell that this is an annuities problem instead of a single deposit problem? Well, first of all, we are talking about that he should make monthly deposits. That's telling you that you're going to make deposits more than once. And when it says how much, that's telling you that payment is what you're looking for. Another thing to take note of is that this goal amount of $40,000, we don't have it now. We will have it in 5 years. So that's what tells me that it's a future value problem. Just like on the last problem, because we now have this fraction and all this fun stuff with parentheses and everything else, we need to find R over N and NT first. So R over N on this problem is 0.015. Because it's monthly, we're going to divide by 12. So we're going to get 0.00125. You may have noticed that all the examples that we are doing together, that the decimals come out nice, they terminate. Many times in your homework, they do not. When you get a long decimal on homework problems, you must use that entire decimal. NT, N is 12 because it's compounded monthly, and it's 5 years, so NT comes out to be 60. Now we're going to put everything into position in the formula. We will have payment equals our future value goal amount is the 40,000. In our fraction, we will have 0.00125 over, just like we did on that last one, we are not going to write out the addition step. We're going to go ahead and just do the addition step. So you will have 1.00125 to the 60 minus 1 in the denominator of this fraction in the brackets. The parentheses are in the formula to remind you to do the addition. We did the addition right off the bat, so we don't need the parentheses in this formula once we've done the addition. This, again, makes your calculator work so much easier by having done it in your formula this way. Calculator work, we're going to do 40,000 times 0.00125 divided by, where you have the brackets, do a parentheses, 1.00125 to the 60th minus 1, close your parentheses. In doing that on your calculator, you should be getting $642.40.